Let's now get our Python code running locally and then deploy it for distributed training and distributed prediction on the cloud. Let's start by invoking Python -m, followed by the name of our module and the name of the class. Let's also specify all of the input arguments that we need. When we run this code, we find that it runs through successfully. And when we carry out an ls command in the output directory, we find that indeed a model has been serialized. Remember that this is because we've explicitly asked the experiment object to serialize the best model into that particular directory location. That directory location, which is inside taxi train slash export slash servo, contains a model, and that model has the name that you see now on screen. It's a number 1513916925, not particularly descriptive. This serialized model is now ready to accept input requests for prediction. To see how this is possible for us to do, let's go ahead and create a simple JSON file. This is a JSON file in which we will write out the values of all of the X variables, for instance, pickup lawn, pickup lat, drop off lawn, drop off lat, and passengers, followed by the corresponding values. Notice that the format of this JSON file exactly matches the format of the dictionary which we would use from within our Python code. A dictionary in which the keys are the names of the features and the values are the values of the X variables. Let's go ahead and use this JSON file, or rather submit this JSON file to our serialized model and see what we get back in the form of a fair prediction. And this is going to make us use for the first time the Cloud ML Engine API. First, let's get the exact name of our model directory. This we get by saving the directory listing of our servo directory, which returns that number 1513 and so on, which we see above. We save this in a variable called model directory. We then invoke gcloud ml engine local predict. This is the prediction service of the gcloud ml engine, but as its name would suggest, we are going to do this with a locally saved model. While invoking the local prediction service of Cloud ML Engine, we also need to specify the model directory as well as the JSON instances file which we just created. And we do get back a nice result. This is a score of 11.51. This should come as no surprise to us because we haven't really changed our model or the training data. So this model is going to still suffer from the same weakness which we saw some time ago, which is that all of the model predictions are going to be close to the number 11. To fix this and to materially improve our model, we are going to have to run a much larger and more robust training data set on our model. So that's what we are going to do next. In fact, we are not even sure that just increasing the size of the training dataset by itself is going to help, but at any rate, that's something that we've got to try. In any case, let's keep moving. Let's now go ahead and carry out a local training process using gcloud ML Engine. This time we will need to specify a package path. This is for Cloud ML Engine to know where to pick up the trainer from. We also need to specify the locations from which it will get the training and evaluation data. And let's also specify the number of epochs, which is equal to 10, and the output directory, which is of course our cloud MLE/taxi trained. The RMSE that we get is still very high, it's 13.76. That's okay. Let's keep going. Let's now go ahead and make sure that we at least have a saved model. This is in our taxi train directory, and we find that it is indeed present there. So we now can satisfy ourselves that the local training process carried out by Cloud ML Engine was successful. Let's now go ahead and carry this out on the cloud. In order to do so, the first thing that we will need to do is to copy the training and the validation data into a cloud bucket. We do this using the gsutil -cp command that will copy the data over onto the cloud. We then can finally submit our job for distributed training. First, let's set a few environment variables, out directory and job name. Let's go ahead and delete the old output directory just in case we had any. And finally, we can now invoke gcloud ml engine jobs submit training. This is followed by a formidable array of job parameters. There is the region, the job directory, and the staging bucket, all of which are exactly as we would expect. None of these needed to be passed in while we were carrying out training locally, by the way. Another interesting job parameter is the scale tier. This is a way of telling the Cloud ML Engine service how much compute capacity we would like to allocate. The basic scale tier is the lowest. As we shall see in a later experiment, we can scale this up to something like standard. In any case, as soon as we go ahead and hit Shift Enter here, our job has been submitted. We can then go ahead and monitor its progress by switching over to the web console and there looking under the ML engine. Like we already discussed, the ML engine is going to write to stack driver logging, so it's easy for us to monitor the log entries from our running job. Let's click on them, and we can see that it's still running 4 minutes and 35 seconds in. We wait, and while we do so, we check on the input parameters passed into our job, and we see that all of these are indeed as we would expect: the region, the runtime version, the eval date, and so on. In any case, it finally succeeds. That's 10 minutes and 20 seconds in. And at this point, we are finally done with a distributed training job. We are now ready to make use of the other service made available by the Cloud ML engine, and that is the distributed prediction service.